All right, so we're looking at this problem here, and we're asked to find the arc length of a single arch of the cycloid, which it was very kind of them, but they did tell us this means the length from 0 to 2 pi. So we don't have to graph it in order to figure out what an arch is. Now remember, a cycloid is when you take a point on a wheel and you like affix a marker to it, and then you rotate the wheel. So it makes an arch like this. So as the wheel goes around, it starts creating a certain shape. And the shape kind of ends up looking sort of like this, depending on where you put the marker on the wheel. If you put it on the rim, it looks like that, where it'll come around and it'll hit the ground, with the ground being the horizontal line. If you place it higher up, then it doesn't hit the ground because that point on the wheel never comes to the ground. So you can get different shapes of cycloids by placing the marker in a different position on the wheel, like on a spoke on a bicycle wheel. So we need to remember what the arc length formula is for parametrics. So remember, for a parametric, the arc length formula goes from A to B, where these are t values, not x or y values. And it's the square root of, let's see if I can remember this right, dx dt quantity squared plus dy dt quantity squared with respect to t. So that's our formula for arc length, I think. Somebody tell me if I've got the wrong one, but I'm pretty sure that's right. So when we're looking at this, then we need to find dx dt and dy dt and then square them individually. So here are our formulas for x and for y. So we can go ahead and apply the derivative to each one of those with respect to t. So I'm going to do x first. So dx dt. Remember that when you do this, the 3 on the outside is just a constant, so it just stays a constant. And then we have to take the derivative of t minus sine t. The derivative of t is, of course, just 1, and the derivative of sine is cosine. So this gives me 3 quantity 1 minus cosine of t. And then if I do dy dt, I get the 3 also as a constant. However, when I look at the inside of this one, the first term is a 1 and the derivative of 1 is 0, so that term disappears. The derivative of cosine is negative sine, so that gives me a double negative, so that becomes positive sine of t. So the derivative with respect to of y with respect to t simply becomes 3 sine of t. All right, now we need to square each one of them. So if I'm squaring dx dt, then this is basically going to give me 9 times 1 minus cosine of t quantity squared. Be sure when you square the binomial that you get the outside and inside doubling. So this should end up giving you 9 times, the 1 times 1 is 1, the outside and inside give you negative cosine t, so you get negative 2 cosine t. And then the negative cosine t times itself gives you a positive cosine squared of t. So that's just your algebra, but it is one of the most commonly missed things that I see. So make sure you square that correctly. And then when you do dy dt and you square that, you should get 9 sine squared of t. Now we put it all together into the arc length formula. And ours is supposed to go from 0 to 2 pi. So our t in this problem is not time, but an angle measure, which is not infrequent. So that's a fairly common thing. So 0 to 2 pi, and then I'm going to throw in dx dt squared and dy dt squared, which gives me and I'm going to go ahead and distribute the 9. So I get 9 minus 18 cosine of t plus 9 cosine squared of t. And then dy dt quantity squared is plus 9 sine squared of t. And all of this is the radicand with the differential dt outside. Your next step is to combine like terms or to use a Pythagorean identity to simplify. And you do have one, it's hidden right here. If you put those together and factor off the 9, you get cosine squared plus sine squared of t, which of course is just 1. And that will give you a plus 9. So you get 9 times 1, which is 9. Then this 9 and this 9 will add together and you should get 18. So now we have the integral from 0 to 2 pi of the square root of 18 minus 18 cosine of t dt. Let's see. Oh, okay. I see why you probably asked about this one. We can get the 18 out of there, but the 1 minus cosine of t is a bit problematic. So I'm looking at it, I can't do a trig substitution because it's not squared. Well, I could, but it would be more difficult. What I'm thinking instead is a double angle formula. So let's see if we can work the double angle formula into this equation. So the one I'm thinking of is the one where sine squared of t would be 1/2 of 1 minus the cosine of 2t. Now I could rewrite this in a different form so that instead of this being 2t, it's t, but then this one would be half of t. So then I could rewrite it as sine squared of half of t, which is 1/2 of 1 minus cosine of t. And if I get the 18s out of there, then I think I can make that substitution. So this is just sort of a trick that you can use to get something that's squared underneath the radical so I can get rid of the radical. And that's probably the part where you got hung up, is what to do with that. So it is just a trick, one of the tricks of the trade. So we go from 0 to 2 pi, and I'm going to have a big square root. I pulled the 18 off, and that left me 1 minus cosine of t. And then I'm going to substitute the 1 minus cosine of t. If I were to take this formula one step further, I could move the 1/2, which is here, to the other side, and I would get 2 sine squared of 1/2 t is equal to 1 minus cosine of t. And that's the one that I need in order to complete this one. So then I have my dt over here. So I guess I'll go ahead and write it one more time. I was going to do it all in one step, but I guess I should rewrite it. So now I can replace that. So I have the 18, and to replace 1 minus cosine of t, I have times 2 sine squared of 1/2 t. Now the 18 times 2 gives me 36, and the square root of 36 is 6. So the 6 will pop out, and it can actually come to the front of the integral. And then I need to take the square root of sine squared. Now, you've got to be careful here, and this could have caused another problem. When you remove sine squared, you've got to think about the integral over which you're integrating, which is 0 to 2 pi, which is a full cycle of sine. But we need to know what cycle is it of 1/2 t, because the problem is if sine becomes negative in that region, then I can't drop the absolute values that should go around sine. And that's a problem, because this should technically be the absolute value of sine of 1/2 t. So then we look at it and we go, okay, well, if I'm going from 0 to 2 pi, where is the sine of 1/2 t going? Well, if I substitute 0, it does start at 0. So I know that much. So it starts at 0 and then goes all the way up to 2 pi times 1/2, which is pi, which means that in effect, it's only going through quadrants 1 and 2. But I know that sine is positive in quadrants 1 and 2, so in fact, I can drop the absolute values. But that's only because my argument is now 1/2 t. So this gives me 6 integral from 0 to 2 pi of sine of 1/2 t dt. From here, you just need a u substitution. So u is 1/2 t, du is 1/2 dt, and then I can rewrite dt as 2 du. So when I replace the dt, I'll get another 2, which can join the 6 on the outside, and that will give me a 12. And then I can also replace the limits of integration if I want to. When t is 0, 1/2 times 0 would still be 0. And when t is 2 pi, u is going up to pi, which is basically what I found out right here. All right, so that gives me my range. So now I can rewrite the integral strictly in terms of u and go from 0 to pi of the sine of u du. Now the antiderivative of sine is going to be negative cosine. So I end up with negative 12 cosine of u between 0 and pi, which becomes negative 12 times the cosine of pi minus the cosine of 0. Cosine of pi is negative 1, and let's see, the cosine of 0 is positive 1, so that gives me negative 2. And once I have negative 2 here, I can multiply it by the negative 12, and I end up with 24 for my final answer, right? So there are a lot of little things you have to think about on this one. It's a little bit tricky thinking about all the different parts of it. There's quite a bit of tricky stuff in here. Thinking about the angle, that's quite tricky, as well as knowing to do this substitution out for the double angle formula in this format. That's also rather tricky. So it can be a little, I can see why you're asking about that one. Okay, let's take a look at another one. Oops, cancel. Let's look at, I think you asked about 19 and 20. So 19 and 20. Okay, so 19, here we go. Put this on a new page. Here's problem 19. We're just supposed to find dy dx and then the second derivative of y with respect to x. There's a formula for both of these, so let me see if I can write them down from memory. All right, it is a Monday. So remember, when you're trying to find the derivative of y with respect to x, but your independent variable is t, we do an abuse of notation, and we write it as dy dt over dx dt. In this sense, if I were to multiply by the reciprocal, the dt's would disappear and it would leave me dy dx. So this is the formula for the first one. Now, when you do the second derivative gets a little bit difficult because both x and y are functions of t itself. So the second derivative formula is more complicated, and it looks like this. You take the derivative with respect to, oh my, what was it? X, I believe, I'll have to check, of the first derivative, or maybe it's with respect to t. Yeah, it must be with respect to t. Of the first derivative, dy dx, which you got from this formula here, and then you divide that by dx dt again, all right? So that's the derivative for the second derivative in a parametric equation. So let me just pause real quick and check the formula just to be sure I've got it. Apply it to these equations right here. So the first thing that we want to do is we want to find dy dx, because we'll need dy dx to do the second derivative as well. So remember that dy dx by formula is dy dt divided by dx dt. So that means take the derivative of each individual equation with respect to t and divide the results. So dy dt goes in the numerator, and that will give us 4 minus 2t. And then the derivative of the x equation goes in the denominator, and that will just give us 16t. Now I would go ahead and reduce this. I could factor a 2 out of the numerator. So that would give me 2 times 2 minus t over 16. And the 2 over 16 would reduce, and I would get 2 minus t over 8. So I would go ahead and do that. And then for the second part, they want us to find the second derivative. So to find the second derivative, we need to take the derivative with respect to t of the first derivative. Hang on, did I do that right? Oh, my bad, I lost my third power. Okay, that should be in there. Where did my t go? I just lost t all the way across, didn't I? My bad. There we go. Okay, I think I fixed it now. Is that correct? Yeah. Okay. Second derivative then of y with respect to x both times would give us the first derivative with respect to t of dy dx. And then we divide again by dx dt. The denominator does not change. So in this one, make sure that when you divide by dx dt that you again use 16t cubed, because that is dx dt. 8t cubed was a reduction of the entire dy dx, but it is not the derivative of dx dt. So I need to take the derivative with respect to t of 2 minus t over 8t cubed divided by, and then use dx dt again, which was 16t cubed. Now, you could rewrite, excuse me, haven't talked much today. You can rewrite the numerator as a product instead of a quotient if you'd rather use the product rule. I would leave the 8 in the denominator, but you could write it as t to the negative 3. So you could, if you wanted, in the numerator, you could take this and write it as 1/8 times t to the negative 3 times 2 minus t. And that might be a simpler form, because the 1/8 you can pull completely outside of the derivative, and then you could apply the product rule instead of the quotient rule, whichever one you prefer. So we can do, oh, I don't know, let's do the quotient rule just for fun. Okay, so in the denominator, I've got 16t cubed, which is going to stay. So the derivative of the quotient, remember your quotient rule, f prime g minus g prime f over g squared. So I need the derivative of the numerator, which is a negative 1, times the bottom, which is 8t cubed, minus, and then I've got my top times the derivative of the bottom. So I'm going to have the derivative of that denominator, oops, not 16, it should be 24, 24t squared times 2 minus t, all divided by 8t cubed quantity squared. Now this is a complex fraction, and you do need to keep straight which one is the true division bar, which is the primary one, which is this one here. And that's why I've drawn it longer than the others. So this is the top of the top, this is the bottom of the top of the bottom, and the bottom of the bottom is not written. But if you want, you can add it just to make sure you keep everything in the right locations. So I can divide by 16t cubed or multiply by its reciprocal. And cleaning up the numerator fraction, I would have negative 8t cubed minus 48t squared. And then what comes after that? Minus 48t squared plus 24t cubed. So I have another t cubed term over, and then I've got 64 because it's 8 squared, t to the 6th. And then multiplying by the reciprocal of the denominator fraction gives me 1 over 16t cubed. Now, I can clean up the numerator because I've got two like terms, negative 8t cubed and plus 24t cubed. So that gives me 16t cubed minus 48t squared. Well, I could clean that up even more if I want to, because it has common factors of 16t squared. So I can pull out the 16t squared, and that leaves behind t minus 3. And the denominator is 64t to the 6th. And this one is 1 over 16t cubed. And then I can do some reduction. The 16s will cancel. And I've got a t squared, which will cancel 2 of those 3 and leave me with t. And I think that's it. That's all I can do. And so finally for this one, that would give me t minus 3 in the numerator divided by 64 t to the 7th, I believe is what I've got. And the answer that they've got in WebWork, they did not clean it up at all. It's really disastrous, but my version is better. This is the reduced form of the solution. And that's what you would get for the second derivative. Okay. All right, let's take a look at the last one Alex had a question about, which I think is number 20. And this is another one where you're finding the first derivative and the second derivative. Now keep in mind, the reason you would look for the second derivative is because you want to know something about where it's concave up and concave down. And the second derivative gives information about concavity. So that's why we're interested in the second derivative. So we're looking at this problem, again, looking for dy dx and the second derivative with respect to x. So now on this one, we'll start with dy dx, and I'll write the formulas as I go. So dy dx is dy dt divided by dx dt. Y is t times e to the 7t, so it's a product of two factors which both have t as a part of it, and that's product rule. So that's going to give me e to the 7t for the first term plus 7t e to the 7t for the second term, just plain old product rule. The derivative of x, however, is just the exponential, but it does involve chain rule because the power on e is negative t, so we'll get a negative 1 popping out to the front. So we get negative e to the negative t. Now, what could you do to clean this up? I always advise to do the algebra at each step before you go to the next step. You make your life a lot simpler when you do that. And if you don't do that, you make your life miserable. First thing to recognize is that the e to the negative t in the denominator is a monomial term. There's no plus or minus between terms here in the denominator. So I could instead lift this to the numerator and think of it instead as a negative e to the positive t, since the negative is a floater and can go anywhere. If I then did that, then I would have to distribute this over the two terms in the numerator, and that would give me a final expression for dy dx of negative e to the 8t minus 7t e to the 8t. Now, once we have this, then we can do the second derivative. So let's put the second derivative formula up here now. We'll use a different color for that one. So the second derivative of y with respect to x both times is the derivative with respect to t of the first derivative, dy dx, divided by dx dt again. So when we apply this formula, remember that we need to take the derivative of the one that we had as the result for dy dx. With the negative. Now you could, if you want, pull the negative outside and put the negative there, and then you'd be taking the derivative of e to the 8t plus 7t e to the 8t. And then you need to divide by dx dt, which was, again, use the original negative e to the negative t. we will be able to do the same sort of trick that we had before. Notice that I've got now two negatives attached to monomial factors, which means that the negatives actually end up canceling and I get a positive. I'll also be able to lift the e to the negative t to the numerator, but I can't do that, or I shouldn't do that until after I've done the derivative of the numerator, just to prevent making an error. So in the numerator, the first term is a simple exponential, but it does involve chain rule because of the 8t. So that will give me 8e to the 8t. And the second term, however, is a product because 7t depends on t and e to the 8t depends on t. So we need product rule. So the first term would be 7e to the 8t when I take the derivative of 7t. And then the second term, I would get chain rule would give me an 8 coming down. So that would give me a 56t e to the 8t. And then I can go ahead, since I've done the derivative, I can think of this being lifted to the numerator and rewritten as e to the t, and it's being multiplied. Once I have that, one base, same base, you add the powers. So this will give me 8e to the 9t plus 7e to the 9t plus 56t e to the 9t. And if I were doing this probably for something else, I would probably factor out the e to the 9t because exponentials can never be 0, and we're often looking for places where it is 0. And oh, I've got two like terms here. I should combine those into 15. And so I would leave it like this, 56t. Because if this does equal 0, it's not coming from the exponential, which means it has to come from what's left behind, which is here. And that would be the end of that problem. Okay. Other questions that you guys had over the homework? You should be by now, let's see, according to the schedule, you should have started your polar coordinates and be done with the basics or working on the basics. And then today you will start area and arc length in polar coordinates. And probably you should be working on that Monday, Tuesday, Wednesday this week. And then we do have one conic sections video that you can watch on Friday or Thursday rather. Now I am a little concerned. I'm wondering, Dawn and Alex, you were in one of the STEM core classes. So I'm wondering if you can tell me how much time you spent on the conic sections part of that course. Did you study hyperbolas, ellipses, and parabolas as conic sections, or did you skip it? You can turn on your thing, not very much. You got to print out and that's kind of it. Okay. Yeah, that's a problem. Okay. Well, then you guys get more videos. So they are included in D2L. I have a video on a circle, just to remind you how to complete the square, and then videos on ellipses, hyperbolas, and parabolas as conic sections. I did briefly review it in the video over conic sections in polar coordinates, but if you've never done it, then you really need to watch those other videos to make sure that you're following along and understanding. Because you probably don't know what a directrix line is then, and you may not know too much about how to find the focal points. So that's something our class spent quite a bit of time on, like almost a week working on. And it will hurt you in that section if you don't have at least a basic understanding of it. Okay. What other questions do you guys have? Questions? Everybody's quiet today. I know it's Monday. Do you realize next week is our last week of class? The end is coming very, very quickly, so we have very little left. How about section 7.3? How is the polar coordinate section going? I will probably emphasize polar coordinates over parametrics, although I'll do some on parametrics as well. And you can have a formula sheet for this exam if you want one. And you are allowed to write down the formulas for the derivative of parametrics, second derivative certainly. No other questions? Okay, it's only 9:35. I'm sure you want to see me do something. Or are you all asleep? Okay. We can take a look at something else. Let's see. I have examples you sent me back to work through still. Okay. Okay. Well, if you guys don't have any questions, we can stop here today and then we can go tomorrow through some of 7.3 or 7.3. That's all you should be. No, 7.3, 7.4. You should be getting into 7.3 and 7.4 pretty quickly. So will there be an exam for chapter 7? Yes, there is. So our exam on this is going to be next week on Wednesday instead of Tuesday. Originally, I had it on Tuesday, but I can email you back your or put the graded exam into D2L, so I don't actually have to see you to give it back. So I'm going to do it on Wednesday instead. So it will cover basically chapter 7, so 7.1 to 7.5, which there's actually quite a bit there. I mean, I will test you on parametrics as far as can you graph one by hand? Can you show me where it begins, where it ends, and which way the orientation is by drawing arrows? Can you find the equation of a tangent line at a point on a parametric? Can you find the first derivative and the second derivative? And then for polar, I'll have you switch from polar coordinates to rectangular coordinates and back. I can also have you on both polar and parametrics convert the equations from parametric or polar back into rectangular or go backwards. Although I don't typically do the other way. I don't typically do rectangular into polar. I usually do polar to rectangular or parametric to rectangular. I can also ask you about tangent lines and polar coordinates. I can ask you about area and polar coordinates, arc length in both, and then I can ask you about conic sections in both. I mean, there's a lot that I can ask you about. Even though it's only 5 sections, it's heavy on material. So that's why I like to kind of do it separately. It's also very different from the rest of the stuff. You will want a graphing calculator or the TI program that you can get for free online. You'll want one or the other for the exam because you're going to need to be able to figure out based on the curve where the polar graph is starting and stopping so you can compute area. I will give you a review, and this time I will try to post solutions for it. I've got to get the last couple of videos made, and then I'll get those out there. But I will try to do that. Okay. Oh, Desmos. Yes, you can use Desmos, Anthony. The problem with Desmos is Desmos will not give you the same information that the graphing calculator will. So that's a problem. Let me show you real quick. I think I can show you what it looks like. Hang on just a second. So it's upside down. There we go. Perfect. Okay. So what I want to show you is what it looks like when you produce a picture on the graphing calculator using the polar coordinate mode. So let's scroll this down so you can see it a little bit better. All right, hopefully that's clear enough. All right, so I'm going to turn it on And you can see I've already got a polar graph in there. You'll go to mode, which is right here. And when you click on mode, you'll go down to the fourth line where it says FUNC for function mode, then PAR for parametric, and what you want is POL for polar. We could have used sequential mode for sequences and series, but I didn't. Once you have it in polar mode, go up here and hit Y equals. So when you go into Y equals, you'll see that I've got an equation in here already, which is the 2 cosine of 3 theta. When you're in polar mode and you hit the variable button, you get the third variable, which is theta. Notice you get the x in function mode, t in parametric, theta in polar mode, and n for sequential mode. You'll also notice over here on the far right, I've got what looks like an old-fashioned skeleton key. So the way to get that is to move all the way over and to hit enter repeatedly until you can get it to look like that. It's actually a hyphen and then a 0. Now, this is the one thing that the graphing calculator has that Desmos does not have, this one option, which is to graph the graph slowly using a circle or a ball to show you where it starts and where it stops. So once I have that set, I go into window, and the window here is going from 0 to pi because that's all it takes in order to draw one picture of the rows. So if I wanted to change it, say to go from 0 to 2 pi, then I could move down to theta max and enter 2 pi, which is usually here on the caret key. That's where pi is. I always leave my theta step at pi divided by 60. It's a good number. It gets me all the ones that we know exact values for, all the pi over 2, pi over 3, pi over 4, and pi over 6s, because 60 is divisible by all of 2, 3, 4, and 6. But it also gives me enough points to draw a smooth curve, but not so many that it freezes the graphing calculator. It's not always the case that more is better. The next thing you do is you hit zoom, and then you want to tell it to pick the best X and Y window. It takes a long time to find the best X and Y window. This is where the graphing calculator and Desmos are superior to us. You just hit zoom 0, which is zoom fit, and it will fit the graph to the best XY window. However, when it draws it, you can see that the drawing looks skewed compared to what I had on there at the beginning. And that's because this screen is a rectangle and not a square. So the tick marks on the X and Y axis are not equal. So what I want to do now is fit it to a square window. So I do zoom fit and then hit zoom again and choose option 5, which is zoom square. Do you see that little ball? And you can see where it started and where it's moving and how it's going around. Notice the ball is now going around a second time. That's how I know that 0 to 2 pi is overkill. I could get one cycle from 0 to pi. Now let me show you what the same thing looks like if I put this into Desmos. All right, so if I go into Desmos, then let me pull up Desmos real fast. Come on. All right, so here is the issue that we have with Desmos. All right, so I'm going to pull it down over here. All right, so you should be able to see Desmos. Now this is rectangular, which is not polar. So you click on the wrench, and then you'll click on what looks like a target shape, and that will give us the polar graph. So I think the one that I was graphing on the other one was 2 cosine of 3 theta. One of the disadvantages is that it doesn't like anything other than r to the first power, but of course the graphing calculator doesn't either. So I get r equals 2 cosine, and then you should use parentheses just to be sure. To enter theta, you just type out the word T-H-E-T, and then I'm going to put A. Do you see what happened when I did that? The graph instantly appeared. I mean, there was no graphing it to show where it starts or where it stops. It was not there, and then boom, the whole thing is there. So you lose the orientation of how it's graphed as theta goes from 0 to pi. Now, why is this a problem? Well, I could ask you to graph this and give me the area between pi over 2 and 5 pi over 6. On the graphing calculator, if I told you to do that, you could come in and you could go to the window and you could say, okay, she said go from pi over 2, so I'm going to change theta minimum to pi divided by 2, and then change theta max to 5 pi divided by 6. And that would give me 5 pi divided by 6. And then when you go graph it, it's only going to graph that part, and it's going to show you where it starts and stops. So what I'm getting there is just the one petal, and I know exactly where it starts and where it stops. So that's an advantage of the graphing calculator over Desmos. You can use Desmos, it's just a little bit trickier. So it can be done either way. You would, down here, you would just simply input pi divided by 2, but realize that as soon as I hit that 2, it's going to give me the graph. Boom, okay? And notice it changed the upper to going to 12 pi. And then if I put in 5 pi divided by, as soon as I hit 6, it's going to give me the graph. It's not even going to wait for enter. There it is. So I don't know for sure whether it's going this direction in a clockwise or counterclockwise. Now there is a way to figure it out, which is as you're coming up this way, your angle is pi over 2, and as it's rotating around this way, can you see that the tangent line is along the 5 pi over 6? So it is in fact rotating in a counterclockwise direction. But depending on the graph, that can be difficult to figure out. So in that sense, I think the graphing calculator has a slight advantage over Desmos as far as knowing which orientation it's graphing. But obviously, the quality of the picture is much better on Desmos. So, all right. So I will stop here and I'll come back tomorrow. If you have more questions, just let me know. Okay?